All right, so let's take a look at some of this information and see if we can start to make sense of it. Now remember, our business guy came to us and he said, hey, we want to make this new product that's worth more money, and we want to make it in your facility using the same process. Now the business guy is normally going to give you some metrics, and in our case he did. He told us that the sale price for the new product is 75% more, or 75% markup as compared to the old product. He also tells us our sale price for our new product is $10 a pound, and if we worked for this company we could probably get the old sale price, but for the nature of this problem I've kind of added a little bit more complexity to it. And then he also tells us that he wants to sell 100,000 pounds of this new product a year. Some other information before we get into this calculation that you're going to need to know is how we're going to make this product. Okay. So for really just looking at it from our level, we're going to assume that everything in our process stays the same. We don't know anything about our process, and we don't have to for this problem. But if you were an actual engineer in the field, there may be some actual things that would change in your process, more than just what we're going to elaborate on here. So same process is used. However, once you start to talk to the chemist, who's normally going to supply you with this type of information, he's going to tell you that yes, it's going to be the same process technology, but the reaction now is not going to be ran at just whatever temperature ambient conditions allow. It needs to be ran at 40 degrees Fahrenheit. He also tells you, which if it's similar to your other product grade, you should probably know, that the reaction is exothermic, which means it's going to give off heat, which in your mind should ring bells off, because if I'm running at 40 degrees Fahrenheit and it's an exothermic reaction, I know I need some sort of cooling media here to keep it at 40 degrees Fahrenheit, because the ambient temperature outside in most places is not 40 degrees Fahrenheit. On top of that, we're generating heat, i.e. it's an exothermic reaction. The chemist normally will give you the heat of reaction. If he doesn't give you that, you're going to need to ask what that is. But he's giving it to you at 500 BTUs per pound of product. Okay? Units are important. If you haven't learned that by now, units are extremely important. So if this were 500 BTUs per pound of solvent, that would drastically change things, and it honestly wouldn't make much sense. But the point I'm trying to convey here is units are important. And then lastly, although we will use this to kind of ingrain in our assumption, at this point in your chemical engineering career, a CSTR probably doesn't mean much to you. That stands for a continuous stir tank reactor. Once you get into reactor design, the assumption that I made here will make a little bit more sense. Okay? So the first thing that we really need to do in this problem set, and remember this problem set is really encompassing not only refrigeration, but I'm making you do an economic evaluation to show you why you need to have these baseline assumptions, these best case models, to quickly evaluate this scenario. This scenario is actually a very real scenario, not exactly, but very similar to one that I was given. And so you're going to have to be able to evaluate the economics of both what you're making and also the economics of what you're going to need to do in order to make that. And that's ultimately what we're getting at here. So let's look at what the economics are for our incentive, our profit. Okay? So I've spelled out everything for you, but if you're watching this video and you have some time, just take a pause and try to see if you can come up with the same formula here for the added profit. See if it makes sense to you. Okay? I really want you guys to really get comfortable with doing things like this, with coming up with the concepts, the logical equations to make these things work. If you're not able to do that, you're going to struggle. Okay? Especially in the real world. So work on that now. If you don't have that habit now, work on it. You can get better at it. So your added profit, how much profit you're going to be making from this new product, is going to be equal to the new price minus the old price times the amount of new product that you're going to make. And so notice here in this equation, if my new price is less than my old price, I'm not going to have added profit. It's going to be a negative value, which would make sense, right? I wouldn't want to make a product that's going to make me less money. So let's go through this. We have all the information here in order to make this evaluation. Now, the one thing that I didn't give you was the old price. I've given you the new price, and I've told you that the new price is 75% markup of the old price. So first, we need to find what this old price is, because I've given you the new price at $10 a pound, and I've given you the amount at 100,000 pounds per year. So, since the new price is equal to the old price times 1.75, or if I were to flesh this out, this would be the old price plus 75% markup. I can then just do basic algebra here, and I wind up with the old price being $5.71 a pound. I'm not walking through this because I'm assuming that by this point you can follow my math. What I want you to take away from is, again, the logical steps here. So now I can come back and find my added profit simply by plugging in my numbers. New price, $10 a pound. Old price we just solved for, $5.71 a pound. Amount, 100,000 pounds per year. Once we do the math, what do we have? Our added profit, or our profit margin here, is right at $430,000 a year. That's going to be important because what we're now going to go do is figure out how much energy we have to take out of this system, then determine how much work we need out of our refrigeration compressor, to then determine how much energy it's going to use, i.e. how much money it's going to cost us to run that compressor. And if it costs us more to run that compressor than what we're making, then we don't have an economic case here to make this new product. It's going to cost us money to make this new product. And if we were just looking at it from an economic perspective, we would say, no, we're not going to run the new product. We're going to keep the old product. Okay? Now, remember, when we're looking at our process flow diagram for our refrigeration cycle, one of the things I told you that we needed was the heat duty on the cold side. And so how can we get that? Remember, it comes down here. We got to keep this reactor at 40 degrees Fahrenheit. So this is going to be the cold side of our refrigeration cycle. And we need to keep this reactor at 40 degrees Fahrenheit, knowing that it's an exothermic reaction, and the heat of a reaction is 500 BTUs per pound of product. So what we need to do is figure out, on this reactor, we need to develop an energy balance to figure out how much energy we're going to have to take out per unit time. And then we can go back to our process flow diagram and put that information and see if it helps us solve what we're looking for, which is ultimately the work of the compressor. How much is the compressor going to cost us to run? So let's look at this. I've just drawn a basic flow diagram here for a reactor. So we have an inlet stream, we have our reactor, we have our outlet stream, and what I've drawn here, this little crooked line that's supposed to show heat transfer. Okay, this isn't mass entering the system, this is just energy transferred between the reactor and some other source here we'll call QC. I labeled it the same as the cold side of the condenser because we know going into this problem this is going to be the cold side heat exchange with the reactor. I've drawn here a system boundary. So if we were to go then and set up our energy balance, here are the terms. Remember, just like what we did with the refrigeration cycle, what do we have here right on this side? We have our accumulation term. Right here we have basically our inlet and our outlet stream, the difference there, the enthalpy difference. We've got two DQ terms here because what I'm trying to represent is heat generated So for instance, we have a reaction that's exothermic, so we have a generation term, and also a heat removal term, which is our QC in this case. I've labeled here, as you can see in this blue, the heat of generation as QR for heat of reaction. Just a simple shorthand. You can probably label it whatever you want. If your teacher has a different terminology here for the heat of reaction, use that. The last thing that we should evaluate in doing an energy balance is any work done to or by the system. We've assumed here that there's no work or no appreciable amount of work going on. We might have a shaft or an agitator in the reactor, but for now, for this base case evaluation, we're not going to worry about that. Okay, we're going to assume no work. Now let's start to refine some of this. Now, one of the simplifying assumptions that I've made here, and in a real life scenario, this may be a bad assumption. Okay? I've really simplified the problem by two things. One, I've assumed that the feed temperature is the same as the reaction temperature. So this temperature coming in is the same as the reactor temperature at 40 degrees Fahrenheit. And this is where my CSTR assumption would come in. Because a CSTR says that the reactor contents are at the same conditions as the outlet. So really what I'm saying here is that there's no temperature change from the inlet in the reactor to the outlet. It's all at 40 degrees Fahrenheit. Now, how is that happening? Because we've got really tight temperature control here. I've also assumed here that the CP value is constant. And so what winds up happening is if we were to evaluate here our enthalpy balance on outlet and inlet, assuming we didn't have a phase change here, our term for heat is Q equals MCP delta T. Since we don't have a temperature change, I've assumed that away, this winds up equaling 0, and so I can cancel it out of our equation. Let me tell you why that's probably a bad assumption. There's a good chance in most industrial cases you're not chilling your feed. Now, you might, but often in the times where you chill the feed, it's often coming in at a lower temperature than the reactor. So this term that I've simplified out may wind up actually being important. I want you to know that because if you're doing this real evaluation, you may want to include that. However, to simplify it for our main purpose of assessing refrigeration, I've done it just for ease of calculation. Because at this point, we're really not trying to do an energy balance on this reactor. What we're trying to do is find out how much energy we need to remove so we can go and do our refrigeration calculations. Now, with that being said, once we've made all of our assumptions here, we've simplified, what we're left with is 0 equals the heat of generation, QR, minus the heat of removal, QC. Simply, QC equals QR. Now, QR can be found because we know that the reaction is exothermic. We have the heat of reaction, and we know how much product we're trying to make. Mass of product times the heat of reaction, 100,000 pounds times 500 BTUs per pound of product, is roughly 50 million BTUs per year. That's how much heat we have to remove from this reactor, 50 million BTUs per year. Okay? All right, so what we're going to do is we're going to go back and look now that we have our QC term, let's go take it back and put it into our process flow diagram and look to see what other information we're going to have to get in order to solve what we're looking for. And remember, that is the work of the compressor. Thank you.